how do we compute this mixed partial derivative? Now, if you are this far in calculus, the problem shouldn't really be in the differentiation itself. Rather, what is the most efficient way to approach this? Because if we take the derivative of this function with respect to different variables 5 times, that is going to take a lot of time. But there is an easier way to approach this, and that is by taking advantage of the properties of derivatives and partial derivatives and mixed partial derivatives. First, what I'm going to do is I'm going to look at my function in parts. So because these are separated by just pluses, I could look at them in 3 pieces. So I have this first piece I'm going to call f1, and then this piece I'm going to call f2, and this third piece I will call f3. And because I'm taking the derivative of the entire function with respect to z, then x, then y, then x, then y, I could distribute that differential into the pieces. So I will have f1 differentiated with respect to z, then x and y, then x and y. Same thing with f2. And then same thing with f3. All I did here is just distribute the differential into the pieces of the function that I split up. Now, it's still not easy to differentiate. Like if I looked at the first function f1 and I attempted to differentiate it with respect to the variable z first, it is inside both sine functions, so I'll end up having to do a product rule and then do that again because I have to take it with respect to x. But I don't have to do that. There's a property of partial derivatives and mixed partial derivatives that allows me to change the order in which I take the derivatives as long as the function is continuous. What I mean by this is if I differentiate the function, for example, with respect to x, then y, then z, it should be the same as if I decided to differentiate it with respect to z, then x, then y. And then obviously, as well as if I decided to differentiate it with respect to y first, then z, then x, and so forth. So I use that same idea and apply it here. So looking at the first function f1, I look at what variable I could use to take the derivative first to make things easier. And my instinct is to do it with respect to y first, because I don't have a y term inside of the trig functions, and so if I take the derivative with respect to y first, it gets rid of the y term, and at this point the function is only with respect to x and z. And because in the question I'm taking the derivative of y twice, I could take the derivative of y again, and then the whole term goes to 0. But for the sake of symmetry, I still need to include the other variables that I am taking, or technically taking the derivative of, even though I won't reach that point because the function goes to 0. But I still, for the theorem to be applied, I need to say technically that I am taking the derivative 5 times. Now we apply the same approach to the second piece. When I look at it, I see y is in that trig function. And again, if I take the derivative with respect to y first, it's going to give me a gross result. And I'm going to have to do more work, but I don't want to do that. So instead, I will choose x because my tan function is multiplied by just one copy of x. So if I take the derivative with respect to x first, then I'm only left with a function with respect to y. So if I take the derivative again with respect to x, then the whole term goes to 0 as well. Oops. And then again, for the sake of symmetry, I will be including the other variables. And as we established, the first function goes to 0, the second function also goes to 0, and then evaluating the third function, I look at it and I ask myself, what variable do I take the derivative with respect to first to make my life easier? And in this case, the only variable that is not included in the trig function is x. So taking the derivative with respect to x first is the smartest idea, because then it gets rid of that x copy, and I have a function with respect to z and y only, and then I could take the derivative with respect to x again, and the whole thing also goes to 0. And so that concludes, in way less steps, that this mixed derivative goes to 0. And that's it.